So from the original diagram of our problem where we had an externally applied force at node 3 and we have node 1 we know is fixed, um, we were able to determine that that our externally applied force at F1 is our reaction force, which at this moment we don't know. F2 is equal to 0 because there's no externally applied force, and F3 is our applied force. Okay, so this leaves us with one unknown force, which we can say is going to be our reaction force. Okay, um, our global stiffness matrix here all right, is a completely known matrix. However, it is always and will always be a singular matrix, which means that the matrix of K global, the inverse, sorry, the typo here. This should be the inverse matrix of K global does not exist and cannot be calculated. So to avoid the issue with the singular condition, we will partition the equation into two, our matrix equation into two parts. We're going to separate F1 from the original matrix, and we're going to separate F2. So we originally had, this was our global matrix. All right. So what we can do is we can eliminate the first row of this matrix by multiplying it out here, which will become this matrix here, and then the second half of the matrix, or the bottom two rows of the matrix, will isolate out, and we can write them down here. Okay. So so now we're left with this matrix here. The issue with this matrix, however, is that the K matrix is non-square, so we can't inverse it. So in order to do that, we need to remove the first column of our matrix. So we need to basically get rid of this part. Okay. So what we can do, all right, is if we go to the next page, all we're going to do is we're going to just multiply these first two values over to the left-hand side, or to the right by U1, and then we're going to subtract those products from F2 and F3. Okay, so we're going to go to the next page. What you'll see is those two products, K1 times U1 and 0 times U1, got subtracted from F2 and F3. Okay, so now we have a reduced stiffness matrix here, all right, that is square, and more importantly, it also has an inverse. Okay, so that's fantastic. Okay, so we can then apply our boundary conditions that u1 is equal to 0, and our equation simplifies down to this equation here. Okay, so we can now take the inverse of k reduced and multiply it by both sides, so that we can then solve for u2 and u3. Okay, so this is our inverse K matrix here. All right, and now remember from the problem, there's no externally applied forces, so we can set F2 equal to 0. So we end up getting U2, these two values for U2 and U3. Okay, so to solve for our unknown force at our boundary F1, we can use the equation we had on the last page that we separated out. So remember, we had separated out this equation here. So we can plug in U2 into this equation. So we get F1 would be equal to K1 times 0 minus F3 over K1, which is our value for U2. Alright, so what we end up getting is that the K1s cancel out, and we get F1 is going to be equal to negative F3, which makes sense. The reaction at the boundary should equal the applied force at the end. Okay, so very good. Okay, all right. So in short, all we did was we took our original global equation. All right, we broke it down into our basically we separated our known forces from our unknown forces, and then we were able to then solve for the unknown displacements, using the inverse of the reduced stiffness matrix. Okay, so we separated our known forces and we separated. So I guess this matrix here is really critical. This is our unknown displacements. All right, this is our reduced stiffness matrix, and this is our known forces. Okay, so using that, we can then solve for our unknown displacements. Once we have our unknown displacements, we can then plug them back in to solve for our unknown forces. Okay. All right. So that concludes how we can get all of our global forces and our displacements from all our nodes. In the next video, we're going to talk about how you can calculate the forces at each node, but also the stress and strain and displacement within the stress and the strain within the element itself.